Okay, so yes, a homework assignment has been posted online, and it should, where is this? Okay, basically, I'm gonna have you guys build up a neural network and apply gradient descent to train the neural network. We're going to use the classic iris data set, okay? And so you're going to take those 4 numeric variables, the sepal length and width and petal length and width, and try to predict which species it is. So there's like Setosa and versicolor and virginica or something like that. I don't know how to pronounce these species, but so that's what we got. Have you guys ever used LaTeX as a typesetting? Okay, so there's a few parts where I want you to kind of just like write out the equations and write out the derivatives or the gradients, and so I recommend using LaTeX. I guess you don't have to, but I think LaTeX makes it pretty. So if you've never used LaTeX before, just type in Wikibooks LaTeX. Okay, it's pronounced LaTeX, and then or LaTeX, I don't know. And then go to LaTeX or LaTeX mathematics, and this tells you, this is how you write symbols and make superscripts and fractions and all of that. And if you want derivatives or things like that, it's all there. Okay. I think the homework, I believe I've made it pretty straightforward. You're going to have to scale your data so everything's between 0 and 1. And then you're going to set up the network to have 4 input nodes. And then we'll have 2 nodes in the hidden layer. That was arbitrarily chosen. We could have just as easily chosen 10 nodes in the hidden layer, but we'll have 2, and then there will be 3 output nodes, 1 for each species, so that when we code the output, it'll be ones and zeros, kind of like the way we did the handwriting digit recognition. So if the species is virginica, then the 3rd node will be a 1, but the other 2 nodes will be zeros for the output layer. Okay, you'll explain the forward propagation and then write that in code, and then you'll do the back propagation, which is effectively finding the gradients, and write that in code. Yes? So if you the what do you call it? Our studio can handle LaTeX, and you can render as HTML. Yeah. So for example, this stuff that I have here, this is written in LaTeX. Okay. So this partial. If the cost function is j, something like this, the partial derivative looks like this, and all you do is in your document, you put it in between $signs. Okay, so if you use a double $sign, it will set that equation apart and center it. So that's this thing right here. So it's just double $sign says, hey, I'm dealing with math, and then you write f of t, and then fraction, where the numerator is 1 and the denominator is this, okay? And then when it renders, it looks like that. So you can incorporate your LaTeX code right in the in your document. If you want inline math, so if you want math, but you don't want it on its own line, you use a single $sign. okay? And it will render kind of like this. So this is how you get mathematical symbols inline here, okay? So yeah, so you don't need to render it as PDF. It'll still render as HTML just fine, okay? And then so you'll do that, and then you'll use gradient descent to kind of train your model. I also have you guys do some numeric gradient checking just to make sure that you've coded up the function for your gradient properly. Okay, you'll probably peek at my code that I've written for the kind of the handwriting neural network and kind of our toy neural network example. You can probably use those to kind of guide you, but you know, my code is also not like the most efficient code. It's just kind of written for simplicity and understanding, and you can code it up however you want. And then at the end, I have you guys install the package NNet, which does neural networking. Neural networks, it's very simple. You just kind of type in and you say, hey, here's my data, go. And you don't have to do any scaling. You don't have to re-express the species as, you know, ones and zeros and things like that. So anyway, it's meant to be a little bit challenging, okay? So work through that. It'll be due next Friday, okay, a week from today. All right. Okay, so we'll yeah.
Is this gonna be our last one, or there's one?
Yeah, I'm debating if I should throw in just kind of a quick homework assignment or not before our final, and I have to figure out what to write for the final also. Just because there's I don't know how long I should make that thing, right? Because you'll only have like what, 2 or 3 days to do the final, so I have to make it of reasonable length, but also I want to make it fairly comprehensive. So this is the hard part for me. Okay. Yeah. Yeah. So the grader, I talked to her. She's gonna work on them this weekend. So, okay. So I apologize. There was a miscommunication between me and the grader. She didn't realize she was supposed to have them graded. So I don't know what happened. Okay. Where did my notes go? All right. But okay. I believe our TA covered a little bit on Newton's method. Yes? Maybe? Okay. And so Newton's method is a way for root finding. Okay, so it's a way to find where the function crosses 0, okay? And so in the context of optimization, okay, so we'll I guess I'll just from a high level definition or high level perspective. Okay, so Newton's method, you know, this is, you know, from calculus. So is a way for us to find the roots of a function or basically where the function is equal to 0. Okay, but for optimization, we want to find like a minimum or a maximum, right? So in optimization, we wish to find a minimum, okay, or max. Okay, so to apply Newton's method for optimization, requires what we call a twice differentiable function, okay? Okay, so basically you take the derivative of the function, or the gradient, if you got if it's multi-dimensional. So derivative of the function, and basically we will use Newton's method to find out where the gradient is equal to 0. Okay, as those will be at least either local minima, maxima, or saddle points, right? It's already the end of February. Just a couple more weeks of class, finals week, spring break, and then spring quarter, right? And then maybe you guys graduate, some of you, and then some of you still have another year, or more, or a summer quarter. Who knows? Anyway, okay. Do I need to get into Newton's method even more, or not really? So basically, to find where the gradient is equal to 0, so, with the function, you start off with kind of a x0 point, and then you take the ratio between the value of the function at that point and the derivative of at that point. Okay, and then you subtract that off, and that gives you x1, okay, and then you just iterate that, right? So just kind of as a recall. So, initial point x0, okay, and then you find and you set so for okay, so for optimization, f of our function is equal to our gradient, and then basically f prime will be our Hessian. Okay, and then so when you apply this to some kind of function, if this is your point x0, you find at this location f of, this would be f of x0, okay? And then you find the slope at that point right here. This is supposed to be tangent, okay? This is gonna, this point will be x1, okay? And you can check it out. This would be x1 is equal to x0 minus okay, and then you just kind of iterate this, and essentially you get closer and closer until you get to some value that's close enough to where it crosses. Okay. If I guess in matrix notation, all right, let's see. We would say x at time t plus 1 will be x at time t minus, and you can think of this as kind of the not g, sorry, f prime of x at time t inverse, so this effectively puts the gradient in the denominator multiplied by f of x at time t. Okay, so with for optimization, this is effectively x of time at time t, so x at time t plus 1 is going to be x at time t minus, so you can think of the Hessian, we'll call the gradient and the gradient squared. I guess we can just say some function g, okay? So this is effectively the Hessian of some function g at x at time t inverse times the gradient of g of x at time t. Okay, so it requires that we calculate this as such. Okay. Sometimes, and we could implement this just straight up. Okay. It would require us to calculate the gradient, which is it's a bit of work, depending on the function that we have, and then it would also require us to calculate the Hessian, which is even more work, right? Because if let's say your function g is a function of x1 through x3, okay, your gradient will now be a vector of basically the partials with respect to x1, partial with respect to x2, and the partial with respect to x3, okay? And then your Hessian will be a 3 by 3 matrix of partials with respect to x1 and partial with respect to x1, and then partial with respect to x1 times the partial with respect to x2, so on and so forth, filling out all of these things. So the calculation of the Hessian could be what we call computationally expensive, right? And so there are kind of some and I shouldn't say cheat, but some approximate methods. So instead of trying to calculate this Hessian directly, we have kind of just approximations, kind of in a similar way where we have calculated when we do the numeric gradient checking in when we do the gradient descent, where we just kind of add a small quantity to get kind of a current estimate of the slope. We can do something similar for calculating the Hessian, okay? And so this is kind of what the Bfgs algorithm does. And I'm just going to point you to Wikipedia. Algorithm. Here we go. Here we go. Okay. So Bfgs, basically, it's an algorithm used for gradient descent, and it's approximating the Hessian matrix. Okay. Do we need to understand all of these details? I don't know. Maybe in a graduate level course, it'd be very good too. I think maybe for our class we can just kind of say this is kind of the big idea of what the Bfgs is doing. If you're curious about it, I recommend doing some reading on it. You can read the original paper, but that might go a little bit. Okay, so these papers can be kind of a little bit dreadful. But if you're thinking of grad school, you got to get used to reading these research articles and papers and just trudge through them. And when I started grad school, it would take me like 3 days just to get through one paper, try to make sense of it. And even then, at the end of it, I would be like, I still don't know if I understand. But then, like after years of being in grad school, you'll be like, oh, okay, I think I understand. No, it gets better. It gets better. But in the beginning, it's like, oh my gosh, because it's just like pages of this kind of stuff, right? And you're like, oh. Okay, so the Bfgs algorithm, we use a numeric approximation to numeric approximation of the Hessian matrix. Okay, and so this is called a quasi-Newton approach for our optimization. Okay, so Bfgs algorithm is kind of like it's like Newton's method, okay, but without having to actually calculate the Hessian. Okay, so it would be okay, so we use a numeric approximation of the Hessian matrix, and we use this along with the gradient to try to find where the minimum might be. Okay. So we use numeric approximation of the Hessian matrix, and this this allows us to find minima, maybe a bit more efficiently. Okay. One of the problems with gradient descent, which we saw earlier in this class, was sometimes you would run into that zigzagging problem. Okay, and that zigzagging problem, I did some more research into it. It's a problem because in that local area, the direction of steepest descent is not necessarily pointing towards the actual minima. Okay, and so so with just straight up gradient descent, sometimes you run into this zigzagging problem. BFGS doesn't completely eliminate all problems with gradient descent, but it helps pick maybe a slightly better direction to travel in. Okay. Okay. All right. We'll just leave it at that. Let's see. Okay. We also have coordinate descent. Coordinate descent is another optimization algorithm. Okay. Okay, and this is all right, and so here, you know, again, we want to minimize some function f, which might be a function of x1, x2 up through xp. Okay, and what we do, what coordinate descent does, coordinate descent minimizes one x sub I at a time. Okay, so so at time so x at time t x of time t sub j. So this is, you know, to minimize the jth x. Okay, this is going to be whatever value of x sub j minimizes the function. So it's you know, to minimize this is you know, pick the value of xj that minimizes the function, and the function at this moment in time consists of, so you start off with x1, so x1 has already been updated to x sub t, all right, but and x of j minus 1. So the one prior to the jth element has already been updated to x at time t, and then this is the value that we are fluctuating or changing, and then everything that comes after j is still using the older values. Okay, so these are not yet updated. And these ones are already, quote, updated. And then we, this is basically fiddle with this one. Okay, and so I'll illustrate what this looks like in the like a two-dimensional case. Okay, so let's say we have some function of x1 and x2. Okay, and then we'll draw some contours. It's hard drawing circles. Okay. So what we want is, so let's say we start off at some point. This will be our initial start point, okay? And this is x1, and this is x2. Okay, so this point right here, this is x sub 1 at time 0, and this would be x sub 2 at time 0. Okay, so we start off with x sub 1 at time 0 and x sub 2 at time 0. All right, and then what we do, maybe I should draw another contour, okay, is we're going to, keeping x2 kind of set at this value, I'm going to draw like a little horizontal line here. We're going to travel along this path. So while x2 remains at x2 of value 0, you know, we update x sub 1 at time 1. We pick to be the value that the minimum value along this kind of search path. All right, and so where's that going to be? That's going to be right here, right? So we've updated. So at this point we now have this is going to be x sub 1 at time 1. Okay, so we've updated this. Okay, and then now that we have this, we're going to we're going to kind of search along this path. So now that we have x sub 1 at time 1, we're going to search along this path and update x sub 2 to be the minimum value along here. And where's that going to be? That's going to be right here, right? Can we see this? Sure. Yeah? No? Am I talking to myself here? Okay, so here, maybe I have to go back. So we started off at this point right here, okay? And then, so we're gonna hold, this is at x1, 0 at time 0 and x2 at time 0, okay? We're gonna keep x sub 2 at time 0 constant. And so that's what this green line represents, okay? Along this path, which is the green path, okay? And so we go along here and we say, okay, along here, where is, what value of x1 should I pick that's going to minimize the values along this green path, okay? The value that's going to minimize our function of x1 and x2 along here is going to be right here, okay? Because we can see that it's touching the contour here, and so, you know, anywhere else it's bigger than that, okay? So right here, so we pick this value of x1, and so now we have x1 at time 1, and we're still at x2 at time 0. Okay? So now that we've updated x1, we're going to hold that value constant right here. So now I've got this orange line, okay, or brown line, whatever color this is, and we're going to kind of search along here. We're going to be changing the values of x2 and say, okay, where along here do I minimize the function x1, x2? Okay, and it minimizes the function x1 and x2 probably somewhere inside here, right? Because this is now, we're already inside our kind of our central circle here, okay? And then so this becomes our x2 at time 1, okay? So this is one iteration, okay? And then now we just repeat the process, okay? And then so we're gonna kind of like search along here and then search along here until we get to some place where it feels like it's converged, okay? So this is coordinate descent. Huh? You know, well, it depends. It depends. You might not, if the thing looks like, you know, if your coordinates and things, so if you get something that looks like this, okay, then you're going to be zigzagging kind of a lot, okay? So it depends on how the contours are set up, okay? So, but the nice thing about this, okay, so here you don't really have to, you just have to search along one dimension at a time, okay? Yeah.
So if you have 3 variables, then you would go 1, 0, 0, 0, 0, 0, and 1, 0, 0, and 1, 1, 0.
Yes, it would start off 0, 0, 0, and then 1, 0, 0, 1, 1, 0, 1, 1, 1. Exactly. Yeah, exactly like that. Okay, and so you can have whatever, a lot of dimensions, and do this kind of thing. It behaves best. All of these algorithms behave best when the function itself is convex. Okay, you know, but research is being done on non-convex functions. But this is probably why the squared error is a popular choice for the cost function, because the squared error cost function is generally convex. Okay, so this works best for convex functions. With just this description, do you think you guys could write a coordinate descent algorithm for a simple two-dimensional problem? I feel like you should be able to. I feel like you should be able to, okay? Yeah, okay, well. All right, well, I don't know. Okay. Let's see. Using coordinate descent. Okay. I guess we can look at applications of some of these minimization algorithms. there are lots of other optimization or minimization algorithms, and I'm just debating how many we should cover, and how in depth we should get for each of these things. Okay, well, I'll think about this over the weekend for you guys. Okay, but we'll leave it at that for this. Works best with convex functions. Okay, so I guess next week we'll look at some other applications, maybe applications of optimization for maximum likelihood estimation. Okay. So we will do this. Okay. You guys are familiar with maximum likelihood estimation already, right? So basically, you've got all of your data. Y1, Y2 to Y sub n, okay? And then basically your likelihood function is going to be the product of the probabilities of each of your data points. Okay? And then, you know, dealing with the product is tough, so oftentimes we deal with the log likelihood, and we just take the log of this and it becomes a sum rather than a product. And we try to maximize this, right? So maximize this. By adjusting the parameters whatever the parameters. So if you get some probability function for like the normal, like if y is a normal distribution, your theta will be your mean and standard deviation and things like that. And you try adjusting those to see if you can maximize the data, okay? But the total likelihood of the data. All right. Okay. Well, so this is kind of the idea. We'll take a look at this and we'll write up some code on Monday for this. Have a good weekend. Good luck on your homework. You know, I would say start early on it rather than wait till Thursday of next week. And so anyway, it shouldn't be too bad. Okay. Have a great weekend. Oh, the Oscars are this weekend. I don't know. Anything else? Yeah. Okay.